Hello! Welcome back to another episode of Barely Working AI. In a lot of my previous videos, we've used language models for a wide variety of applications. We've used language models to generate stories, as well as music. But what are language models exactly? Well, this is the question that I hope to answer in today's video. More specifically, I hope to explain the structure of language models and how to use them effectively. However, before watching this video, I recommend that all viewers please watch my previous video on neural networks first, as this will cover a lot of information required to understand this topic, which I will only briefly summarize here. So, with that out of the way, let's start by defining what language models are. Language models are systems that serve the purpose of predicting the next occurring word in a sequence given prior context. A language model will take in a series of words as input and will output a probability distribution indicating what words are likely to occur next. Modern language models are based on neural networks and are trained on large amounts of running text so that they acquire a good understanding of a language. These neural networks are used in everything from chatbots and question answering systems to creative writing applications. Any system that needs to write anything probably uses a language model. Now that we've defined what language models are, let's talk about the structure of language models. To understand language models, we need to first understand three of their primary components. More specifically, we need to understand what an embedding layer is, what hidden layers are, and what a model's output layer is. Let's start by talking about the first of these components, the embedding layer. When we input words into our language model, our system needs to understand what they mean. For this, we use an embedding layer. An embedding layer is typically the first component of a language model. It serves the purpose of converting input words into vector representations of their meanings. Essentially, what this component does is encode each word input into a neural network into a long series of numbers that represents what that word means. These series of numbers, or vectors, are referred to as word embeddings, as the name of the embedding layer implies. Each word in a model's input vocabulary will have an embedding associated with it. Typically, at the start of training, these word embeddings will be set to random values, but through our training regimen, we hope to learn appropriate values for each vector. To summarize before moving on, the embedding layer serves the purpose of encoding input words into vectors, which represent what each word means. Now that we've discussed the embedding layer, let's move on to our next component. The next component of a language model, after the model's embedding layer, is typically hidden layers. The hidden layers of a language model do the heavy lifting. These hidden layers serve the purpose of further encoding our input sequence to drive a more holistic representation of its meaning. Essentially, they encode the meaning of the entire input sequence rather than just a single word. Typically, a language model will have many hidden layers. Given the output from the previous layer, the next hidden layer will further encode their meaning, resulting in a more complex representation. Each one of these hidden layers is composed of many individual units referred to as neurons. These neurons can have many different architectures. For the purposes of this video, I will summarize three types of neurons that you are likely to encounter in a language model. The simplest type of neuron is feed-forward units. These neurons are composed of weights and biases that can be used to calculate their output using a simple weighted summation. However, in modern natural language processing, it is far more common to use self-attention transformers, or if you're really old school, recurrent neural networks. Self-attention transformers are a type of neural unit that work by comparing an input at the current focus of attention in the case of language models, the most recent input, to all previous vectors in a sequence to find the most relevant information for the current prediction. Essentially, these units compare the most recent word in a sequence to the rest of the sentence when making a decision. Like feed-forward units, self-attention transformers are composed of learnable weights, but they're organized differently. Self-attention transformers are the highest performing neural architecture for language models. For reference, these are the type of neural units used in things like BERT, ChatGPT, and GPT-3. The final neural architecture I want to discuss is recurrent neural networks. Recurrent neural networks have largely been phased out by self-attention transformers. Recurrent neural networks operate over a sequence, passing context forward. However, as they operate over a sequence, they can often fail to model long-range dependencies, as information at the start of an input sequence can get lost. I bring up recurrent neural networks here because before self-attention transformers, recurrent neural networks made up the hidden layers of many historical language models. To summarize, a language model typically has many hidden layers. These hidden layers are composed of neural units and are used to further encode the meaning of the input sequence. The final component of a language model that I want to talk about is the output layer. The output layer serves the purpose of telling us which word is likely to occur next, given all information from the previous layers. Like the hidden layers, the output layer is composed of neurons. For each word in a model's output vocabulary, there is a neuron corresponding to it in the output layer. The output for each of these neurons will be the probability of the word they are associated with occurring next. Essentially, the output layer gives us the probabilities of which words will occur next. To summarize everything that I've talked about, the embedding layer converts words into representations of their meanings. The hidden layers take these representations and use them to encode the input context, and the output uses the hidden layers' outputs to make a decision on what words are likely to occur next. Now, we understand the structure of language models, but how do we learn the weights for each layer? Each layer of a language model is composed of learnable weights. The output layer and the hidden layer are composed of neurons, while the embedding layer has numbers associated with each word that we have to learn. To learn appropriate weights and biases for our neural network, we have to train it. To train our neural network, we try to teach it to minimize an objective called a loss function. This loss function is calculated based on some training data. So, essentially, we attempt to set the numbers or weights in our neural network to values that minimize this loss function when calculated over our training data. Typically, for a language model, the loss function we use is cross-entropy loss. By minimizing this function, we are maximizing the probability that our language model makes the right decision. To train our language model, we require large amounts of data. The more data we have, the better our neural network will perform. Now let's talk about how to have fun with language models. Typically, we train language models on large amounts of data. This process is called pre-training. You can find pre-trained models everywhere on the internet, but these language models oftentimes can't generate the type of output we want. They will probably struggle to write the kinds of books you want them to, or generate the type of dialogue you want. But we can fix this. By taking a pre-trained model, we can adapt it through transfer learning to suit our needs. By showing our pre-trained model more task-specific data, we can train our language models to do virtually anything we want. You can teach it how to generate Harry Potter books, Star Wars scripts, or even new SCPs. Pretty cool, right? Anyways, that's it for today's video. We've covered the basics of language models, their structure, and how to train them. If you found this video helpful, please leave a comment down below. Thank you all for watching.